In this unit, we will discuss heat flows through that building shell. To accurately calculate our heat load, we need to know what heat gains and heat losses we have in the structure. To maintain home comfort in the cooling season, we need to remove heat that's been gained by transmission through the building shell, as well as solar heat gain through the windows, heat gained through infiltration of the hot outside air, and heat generated by appliances, equipment, lighting, and other internal heat gains. To maintain that comfort in the heating season, we again have heat moving through our building shell, through the floors, walls, and ceilings, as well as exfiltration of that conditioned air to the outside world. However, those solar heat gains through the windows and the gains from the appliances, equipment, lighting, and other internal heat gains actually help lower our heat load during the winter. So the heat supplied by our heating system only needs to make up the difference. Heat loss and heat gain through our home's envelope are the largest energy demands on residential buildings. To maintain comfort, our heating and cooling systems must supply or remove heat at a rate that's roughly equal to the rate that the heat flows through the building shell. To calculate these flows, we need to know some values. K value is a property of a material. It is the material's thermal conductivity. R value is pretty common and known to most of us. It's a material's resistance to heat flow. U value is a measure of thermal conductance, but across an assembly of materials, not as a property of a single material. U value and R value can be thought of as the inverse of each other. If you take the number 1 and divide by U, you will get R. If you take the number 1 and divide by R, you will get U. A material's thermal conductivity is measured using a 1-inch thick by 1 foot square slab of the material, determining the rate of heat flow when there is a 1 degree Fahrenheit temperature difference on each surface of the material. Generally, conduction has an inverse relationship to a material's thickness. As the material's thickness increases, its conductivity decreases. It takes longer for the heat to transfer completely to the other side. Conversely, when the material is made thinner, the heat travels through to the other side faster because it does not have as much material to travel through. Materials with high conductivity are called conductors, while materials with low conductivity are called insulators. You can see on the chart that aluminum, steel, glass, concrete, and brick are all considered conductors. Rubber, glass, wool, and air are all insulators. Wood provides a transition point between being more conductive than the insulators and more insulating than the conductors. You can see that air is an excellent insulator, and this is why insulation's job is to trap air in the correct density to insulate and slow the heat loss in our buildings. Building shell components contain a variety of materials when looked at in cross-section. A wall will have wood studs, some sort of insulation, sheathing, siding, drywall, etc. A stud frame wall is about 20% wood and 80% insulated cavities. The wall's U value takes this all into account as an area-weighted calculation of the conductance of the overall wall. So if we have the thermal conductance and we know the temperature we're shooting for versus the temperature we wish to maintain within the structure, then we just need to know the area of the wall and we can calculate that wall's heat load. The heat load calculation is UA delta T. The U value of the wall times the area of the wall times the change in temperature from one side to the other. The answer will be in BTUs per hour. Heat load tells us the amount of BTUs transmitting through the assembly, our UA delta T, and is expressed with a lowercase q. We use heat load to help properly size equipment. Heat loss brings a time variable into the equation and gives us those transmission losses over a certain amount of time. Heat loss is usually calculated on a seasonal basis over a heating season or over a cooling season and is used to calculate improvement payback and the soundness of an investment. All this work done to quantify building energy flows is done for one of 3 reasons: to estimate heating and cooling costs, calculate potential savings from energy efficiency improvements, or to properly size heating and cooling equipment. An understanding of the building envelope or building shell is critical to quantifying and understanding the heat flows through that shell. You now have a better grasp of the components and the calculations used in that quantification.